Great to meet you guys. Cody Davis from Electric Power Engineers here to talk to you today about the distribution modeling process, which uses all of the very complicated forecast things you just heard about as an input to try to model and understand what's going on the individual components within power systems. So we're going to talk about what the inputs and assumptions are, what the specific tools and methods are associated with distribution modeling, and then open it up for questions. So when we talk about distribution modeling, you may also hear it as like a power flow model. This is a digital representation of what the distribution network looks like in terms of connectivity and demand. We're using, again, sort of known or measured information to determine some unknown values or to study the effects of system changes. Lots of different types of modeling: distribution planning, modeling, protection coordination, subtransmissions, dynamics. But kind of regardless, the accuracy of whatever you're doing and whatever your analysis is depends on the accuracy of the input data and the underlying inputs to the model. There's a bunch of different modeling tools. We're going to focus mostly on distribution planning today, which is your Synergy, SIME, Windmill, Dig Silent internationally, and like OpenDSS is more of the research side. SIME and Synergy, most common ones for larger utilities, cooperatives and smaller utilities like Windmill and MillSoft. There's also protection coordination. Aspen, ETAP, and CAPE are most common there. For subtransmission networks where power flows are more complicated and you have sort of networks of interconnected parallel operating equipment, PSSE is pretty much the most common. There's some other options as well. And then for dynamics, like PSCAD is really the biggest one. But we're going to focus mostly on the planning side. So within distribution planning modeling, the core concept is to sort of establish your baseline state of truth and then sort of make some changes hypothetically to see what's going to happen. And this is the same approach used kind of regardless of what we're doing. You'll see it in voltage drop or power flow analysis, DER interconnection studies, contingency analysis, and switching and VO. And it all starts from this sort of understand what's going on now, make some changes, and see what happens. So in terms of modeling process, again, we're talking mostly in terms of inputs. So collect your input data, check it, and make sure it actually makes sense. Go through the sort of data cleanup process. Do you have things that are missing? Do you have things that are errors? Redo it again, check it again, make sure it sort of makes sense. And then we can go into model setup. And then we do the same thing. All of the input data from all the different systems that we'll talk about needs to exist. It needs to make sense. It needs to make sense together and give you a sane, sort of reasonable place to start from. We have another cleanup phase, and then we actually do a study. So what are these inputs and assumptions? There's really a couple of big ones: GIS, components, connectivity, device settings. What equipment exists and where is it is really foundational to modeling. The second are the measurements, so power flow measurements from SCADA or from AMI that tell you how much power is flowing through all these different points and where, any kind of voltage telemetry or other stuff that you have. And then some environmental factors as well, things like temperature data, irradiance data that may be useful, especially for DER. So when we talk about component information, again, GIS really kind of comes through the biggest here. We want to know what type of thing is out there, how is it connected, where is it, what sorts of parameters are associated with it. Most commercial modeling software like Synergy, shown here, or SIME, has an equipment warehouse that translates sort of GIS names, like for example, 1-aught AAAC conductor, into actual electrical properties. So impedance per mile and physical configuration and all the things that you need to go from a name of a thing to the actual performance of the thing. Engineers may also model like a transmission source with a substation, or you may just see individual feeders. Sort of how substations get modeled can vary depending on what's in GIS and what's sort of maintained separately. But generally, again, you're sort of taking all the equipment that exists, putting it where it's supposed to be, and connecting it how it's actually connected is the goal. Load data sources, again, SCADA is the biggest one. This provides usually mostly load, real and reactive power data. You also get some voltage measurement data, but usually mostly on your bigger components. So circuit level feeder exits or substation transformers, sometimes like line recloser devices, especially for like Flizzr type of DA implementations. AMI is also a good one where you have these advanced meters. You can get interval data that says this is your demand, this is your energy, and other readings there that can be really useful. As Chris talked about a lot, forecasted load growth is really important, but usually done separately and sort of you pulled in as an input. And then GIS has the connectivity. One of the questions was like, how do you know how to trust or how accurate the underlying data is? It's a really, really big challenge. Accurate modeling requires accurate information. We'll talk about some techniques to try to manage some of that where you have these types of issues. But on the right here, you'll see an example of a relatively simple feeder with 3 different phases where you've got customers connected to a phase. You have 3-phase customers connected to all 3. You've got a 2-pot bank down in the bottom right that's only connected to B and C phases. Yes, that does exist. You can get 3-phase service from 2 phases through electrical magic. But they do exist. So all of these sorts of connectivity, who's attached to which transformer, who's attached to which phases roll up to which protective devices, all of that connectivity is really important in doing modeling, especially in the setup. All right, sources and inputs for generation data for DERs in particular. The biggest one is the nameplate. It defines what the maximum capabilities are. It gives you a basis to start from. You can also have specific output or operational settings, things like smart inverter settings, volt-var curves, volt-watt curves, any specific sort of performance requirements are all in there as well. Sources for output data. Chris mentioned PV watts, which I love. Got lots of great data there. Important note for PV watts, it's historical sort of mean temperature. So it'll tell you a January 1st or a June 30th at noon. It's not any particular June 30th at noon. It's normalized. So if you're using it to tie back to specific time series data, they may not necessarily align all the way. So there's a lot of complexity in sort of choosing which data sources and which data sets and how you use them. But it's a really, really good tool to sort of estimate DER production, and there's different ways to try to do that too. All right, so when we model DERs, this is a big one. Generally, most utilities are modeling DER as a separate standalone component in the distribution model. If you look on the top right here, how it's actually set up, you have the distribution system, you hit the meter, and then you've got your sort of loads over here and your DER over here. Well, modeling it that way is really complicated. A lot of utilities don't model the secondary side of the meter at all. So you don't have that sort of load versus generation infrastructure to attach it to in the model. So a lot of times you take what seems like a reasonable shortcut and you just drop the DER immediately on the primary. Say, well, we're gonna pretend it's connected to the primary and it's mostly fine. And it is mostly fine, but it can create some potential challenges, especially where you get some double counting. So for example, if you're using AMI meter data for the load, and then you have the PV on top, you've got the PV contribution in there twice. And we'll talk about how load data gets used in this process, but how DER are mapped and modeled and how that informs power flows and how you prevent this sort of double counting is a really important question that's buried very deeply in the sort of like engineering manual planning experience that it's really hard to get visibility of. There's also some potential impacts like fault current and protection. I'm gonna gloss over a lot of those analyses. They do happen, they are important, but the planning piece tends to drive a lot of the requirements, especially in kind of what we're talking about. Modeling DERs gets really complicated because they are variable in nature. Modeling things like PV is hard, but relatively easy because it's driven by an external sort of driver. There's an environmental factor to consider. Modeling things like storage is a lot harder because the customer can do literally anything with it. So if you don't know what they're doing with it, or you have to guess, or there's not a program, it can be really difficult to say what specifically they're doing with it at the time and how it's going to behave. Building off DERs comes into play a lot in like interconnection studies, but modeling sort of queued applications is a really important aspect of modeling. So when you have a new DER applicant that comes in and says, I want to build a 2 megawatt system at location A, there may already be 2 or 3 existing DERs that have applied that are ahead of them in the queue. So in addition to modeling those DERs that are sort of ahead of them in this sequential processing, there may also be system upgrades associated with those DER that you also have to model, basically to try to sequence who's going to interconnect to the grid and when and what sorts of changes are associated with those. This requires this sort of multiple scenario approach where you're sort of staggering it into, all right, this is what happens when the first one comes in, this is what happens with the second one, this is what happens with the third one. Well, sometimes they don't make it all the way through the process, or they get close to construction and they withdraw. When you're the third one and the first one pulls out, now you've got to restudy all of the other ones as well. So building that sort of planning into the modeling is really important, sort of tracking what those upgrades are that are associated with these and being able to manage that effectively in the modeling process is really important. Okay, this is another sort of semi-technical piece that gets sort of lost in the details a lot of times, but interoperability of different types of data sources is really important for distribution modeling tools. Middleware is a type of software that's used to feed data and information from sort of the relevant sources into the model. SIME has their SIME gateway. Usually vendors have specific scripts or tools or integrations that pull specific data in and use it in specific ways, things like a data lake. These can be relatively simple. They can be really complicated just depending on how much data you're pulling in, where it's coming from, what the sort of structure and labeling looks like for that. One of the big challenges with AMI data and pulling it into PowerFlow tools is some of the internal process walls and accessibility that's there. It may be siloed, it may be very protected. It may be difficult to pipeline that data from AMI into the PowerFlow tools. There's a lot more sort of internal challenges to just getting all this data and putting it together, which is why a lot of utilities, despite sort of being obvious that you should use AMI data in modeling, it can be a lot more difficult than just sort of deciding to do that. Okay. So next we're going to talk a little bit about the specific tools and methods. So in the model setup phase, the keyword for this section is load allocation. This is the process of distributing our measured load at the feeder head across the meter locations and basically all of the points within the model to let us run a power flow. We're going to dial the clock back about 10 years to assume you have one measurement of data at the feeder head initially. You have SCADA, you're spoiled, you have a specific meter that you can read. It's not just a guy with an ammeter driving out there when it's relatively hot and saying that's the peak load. So we have one point of truth, and the rest of it, we have to try to figure out how much load is where on our network. That's the sort of foundational problem of load allocation, and then we'll sort of get to how it's advanced with more data over time. But in this process, we're using a lot of inputs. We're using load data at the feeder head. We're using substation voltage, distances, impedances, all the GIS information, device settings, load data, customer types. All of this feeds in. So you see kind of a sample feeder of all the different things we're considering in load allocation here on the right side. Small CNI customers, small residential, primary meters, DG, you name it, it's out there somewhere. This slide looks really intimidating. I promise we're going to dive into each one of these in detail and make it a little bit more accessible. But there's really three primary methods to doing load allocation, to try and understand how much load is where within the distribution system itself. The first one, and sort of the oldest, is the connected capacity method. This sort of have our demand measured at the feeder head, and we're using sort of a proportional approach to allocate that capacity based on the amount of capacity that's connected in all the various places. The service transformer size is the most sort of classic example of this. So we'll see an example of this in a minute, I promise. We're sort of going from the more historical to the more historical, less data, to a more advanced approach as we go. The limitations of this method, usually the load's not always proportional, and the actual loading and energy consumption might vary quite a bit. So we'll see that in action here in a minute. A build kilowatt hour method is a little bit more data driven. Specifically, we're sort of allocating load based on how much energy a customer is consuming in a given month, which is potentially a much better indicator of how much relative load that they're using than just the service transformer. Service transformers, you may have sort of a minimum size where Like one customer may be connected to a 25 kVA transformer on this area, or you might have 7 customers in a different area. That transformer may have been sized 40 years ago, and that customer's not even there anymore. So like transformer sizing is sometimes not the best method of trying to say how much load is in a given spot. So build kilowatt hours is a good method to do this. It's based more on the actual consumption that you're seeing year over year. This data is very available and it's very accurate. This is the best data source in terms of utilities that they have in terms of accuracy. This is what gets billed off of. There's a lot of incentive to get all of this data right, and it's much more accessible pretty much to every utility that's out there. So very accessible, relatively good indicator of relative loading. Has some limitations, especially as we get into sort of more modern distribution systems. It's less effective for time series analysis because you have, over the whole month, you have one value. So you can't really differentiate. Even if you have SCADA data that says things change over time, this doesn't try to change anything over time. You're just changing the weights stay the same, which can drive accuracy down. Embedded DER also reduce the accuracy of this method. If you've got solar PV behind that meter, anything that you're self-consuming doesn't show up here, right? So you may miss some of the load, or you may sort of misallocate as a result of that. So DER has some challenges to this method as well. The last method we'll talk about is the actual load method, which seems like a no-brainer. Is like, why doesn't everybody just use actual load if they have it, right? Well, this is sort of using the AMI data. I measured 5 kilowatts at this time. I'm gonna assign them, you guessed it, 5 kilowatts. There's a lot to like about this method. There's a lot of good stuff there. However, first, this requires AMI interval data. You have to actually have it. You have to have it reasonably accessible. You have to be able to connect into the database and pull it in and do some timestamp stuff, which becomes a lot more complicated. There's also the potential for overfitting. So when you have this really granular data, that snapshot that you're taking may not actually be representative of what you're trying to model in the future, right? It's very focused on specifically what was happening at the timestamp you're looking at. Well, if the peak shifts a couple of days or a month, that individual customer's behavior may be different. It may not be close to the same. Whereas build kilowatt hours kind of merges all of that like fluctuation out over the month, where it sort of doesn't try to overfit it too much. There are some challenges there. Overall, actual load, if you can use it, usually is the best method just because it's the most accurate, but it does come with its own challenges too. Okay, so I promised examples. So we're gonna start with the connected capacity method. So if here we have our 5 sample transformers, we are assuming about 1,000 kVA of demand spread across all of these transformers of various sizes. So if you look here, we've got transformer 1 is rated at 200 kVA. Transformer 5 is rated at 400 kVA. We are allocating twice as much load to transformer 5 as transformer 1. Everything is allocated proportionally based on the size of the transformer. So we have 1,000 kVA of demand. We have 2,000 total kVA of transformer capacity. Every transformer gets half their capacity assigned as load. Relatively straightforward, but this is how the connected capacity method works. Build kilowatt hours method. You can see this one gets a little bit more complicated. We have a very small sample feeder here with a demand of like 25 kW. We have a variety of different customers that are all billed a variety of different kilowatt hours for this month. And you can kind of see if you just compare, for example, customer 1 and customer 2, 892 kilowatt hours versus 520. Customer 1 has a higher degree of allocated portion of that demand. And if you add them all up, it's again percentage based, but it's tied to the specific customer and their percent of the load, the sort of total energy used in that space. The last method is actual demand. So in this one, we had an aggregate like peak measurement of 102 kW. You'll see that on all of the individual customers, the meter says 14 kW, I allocate 14 kW. The meter says 16, I allocate 16. And you'll see all of these add up to be 100, but my circuit measurement is 102. That misalignment is intentional because you're taking all of the individual meters themselves, there are losses in the network. So there are these other kind of factors that you don't see that are also impactful. So that's how this actual demand method works. You take the actual data that you have, you use it, and you sort of fit everything else around it. All right, so now we have a model that's set up. A lot of effort to get to this before we actually have any conclusions, but that's the process in a nutshell. So when we talk about power flow analysis or load flow analysis or a voltage drop calculation, a lot of terminology that all means the same thing. Basically, we're trying to determine what the voltages and what the currents are at every location on the distribution system. That's the output of this model. So if I pick a spot, I can tell you what I think the voltage should be there and how much current is flowing through that particular wire at whatever snapshot I'm looking at, even if I don't have telemetry there. That's the goal of the model process. For protection studies, usually things are a little bit different. These are based on like short circuit fault currents. What happens if you have a squirrel or a tree branch or a kid's bike chain or anything kind of wrap across the phases or go phase to ground? There's sort of different modeling parameters there. One of the key elements I wanted to talk about with power flow analysis is balanced versus unbalanced power flow. So the three-phase distribution system that almost every distribution utility uses is almost always operated in unbalanced, which means that A phase and B phase and C phase don't all have the same amount of power on them. You've got some customers connected to A phase, you got some on B phase, you got some on C. It's relatively balanced. Usually you want to try to do balance, but you don't always achieve that, and it's not always possible to. So this example, the top circuit here has balanced load 100 kW per phase. The bottom circuit with unbalanced load has a 20 kW imbalance between A phase and B phase. This is relatively typical. Usually you try and stay within about 10%. Well, you can run a power flow assuming unbalanced or balanced, and then sort of force your model to match that. So what that means is, even if my system is operated as unbalanced, I can build a model that says, well, I don't know very well which customers are on A phase or B phase or C phase. I don't really trust my GIS information. I just want to run a balanced and sort of gloss over some of those potential differences. You can do that. That's a technique that's been used. Balanced power flow is really useful where you don't really trust the underlying data. It'll give you a relatively conservative amount that sort of builds in some of that differentiation. So it's going to be less conservative. Usually you're also derating results based on that because you expect some actual imbalance. So you can sort of force that thing you don't know out, run it as if it's balanced, and then sort of reaccount for that error yourself when you're making decisions. Balanced power flow is usually bad if you can get away from it. Unbalanced is better because you're actually modeling what's actually happening. But there are times where balanced power flow is really useful. So yeah, particularly balance does not represent the unbalanced sort of single phase laterals well or really at all. Okay, so a lot of what we talked about is sort of relatively simple historical, the way that almost all the power flow runs have been done since there's been power flow software and engineers were calling GE in New York to put stuff into their computer. Time series power flow is the new interesting thing that is sort of moving towards directionally. It takes this sort of snapshot approach, single run that we were talking about, and just runs a whole bunch of them over and over again. So when you see a 576 analysis, which is 2 24-hour days for an entire year, that is 576 power flows run back to back to back to back to back. 8760, same thing, 8,760 hours in a year. We are running 8,760 power flows in a row and just generating results attached to each one of those instances. For each one of those, we're starting from like a SCADA load profile or something similar, saying at June 1st at 2 p.m., my load was 5.5 megawatts. At 3 p.m., it was 5.6, et cetera. You're just rerunning the power flow with these varying results and generating all of the results for all of these instances themselves. it's a lot more complicated to try to set up and run time series analysis. You need a lot more data. The pipelining, the input's a lot harder. Just doing the sort of data processing and engineering understanding off of it when you have that much more data, it's a lot more complicated because there's just so much to look at rather than looking at an individual hour and saying, oh, I've got this overload here and this voltage issue over here. You've got to look at all of those snapshots and say, all right, these 75 cases, we had some kind of overload. What did I see? Where is it at? How severe is it? That becomes really, really difficult to do and can be if you don't have the right tools. So I mentioned 576, 2 24-hour periods per month. Usually this is either a peak day and a minimum day in that month, or it could also be differentiated by sort of your average weekday versus your average weekend day. Both of those have been done with this before. It depends on like what you're doing, kind of which one you choose, but that's the 576 in a nutshell. This graph over here on the right side is a flexible connection study that we did that I think is a really good relative heat map of how to look at this type of data in a way that is reasonably interpretable. So this is hours of constraint and how much energy curtailment a solar facility would expect in each one of these hours throughout the year. So you can see a lot of the curtailment is concentrated in March, April, May during the solar production timeframe, about 9 to about 2, 3 p.m. in the afternoon. How to present this data, how to show it, how to engage with it is one of the big challenges, especially as utilities try to communicate it out to others, whether that's in studies or in integrated distribution plans. Talking about the results of these types of studies and how that data gets presented is a really important way of sort of making sense of it and deciding what to do from there. Okay, so closing out, actions that states can take around distribution modeling, encouraging utilities to drive towards adopting time series analysis where practical, reviewing existing modeling practices, looking at available data, especially around SCADA and AMI. How many feeders actually have SCADA data is a really important question. The answer is not 100%. In some cases, it's less than 50%, or at least it used to be. There's been a lot of progress there. Driving adoption of modeling, data, and process improvements. All of these models are used in decision-making later on in the process. So having accurate ground truth sort of models is really important to deciding how you make investments or where you have issues as you go forward. State energy offices, again, recommend modeling practice improvements and participating in technical working groups on this. Questions to ask, what type of modeling software are you using? How much do you trust the data that you have in your GIS system or in your sort of connection database? What sorts of assumptions and data are you using around DER performance? How are you modeling large loads? What load allocation method are you using? And how are you sort of implementing that? Are you using balanced or unbalanced power flow? What are you doing with time series analysis today, et cetera? And then it's like, what are the barriers to getting from current practice towards more implementation of this sort of time series approach? All of those, I think, are important questions. I appreciate you sticking with me. It's a very technical, in the weeds type of topic. I'm happy to answer as many questions as you guys have. Yeah.